All right, go ahead.
You can see my screen, right?
Yes, we can see.
Okay, so today I'll be talking about this paper, Neural Thermodynamic Laws for LLM Training. These are the authors of the paper, and this is the reference to the paper. Sorry. So this is the outline. I'll give you a little motivation for the paper, and then the river valley landscape, which they discuss. And then there are two kind of dynamics, slow and fast dynamics, and finally the summary of the paper. So the outline of the main talk here is that large language models, these LLMs, are somehow related to the thermodynamic systems. They say that both are connected, like both have this large number of interacting degree of freedoms, and they're governed by stochastic dynamics. So what the authors propose here is a neural thermodynamic law, which can be used to map the learning dynamics in LLMs via these thermodynamic variables such as temperature, entropy, heat, and work. So the idea is that if we can use these thermodynamic laws, then probably the learning rate, which is generally decided using some hit and trial, can have some better physics laws to govern how to use the learning rate in the system. So what the paper proposes here is that we have a thermodynamic framework to analyze these LLM training. So basically, this stochastic gradient descent can be mapped by the thermodynamic processes. And what they do is there is two kind of training. One is fast. So you have fast dynamics and slow dynamics. And they treat these two degree of freedom separately. So they first talk about fast dynamics and then about slow dynamics. And they try to introduce the analogies with, via these temperature, entropy, energy, etc. Okay, and to provide this framework of neural thermodynamic laws, the toy model is a river valley laws landscape where they studied via both isotropic as well as anisotropic curvature. And experimentally, they verify their analytical theories using the GPT-2 training model. And they derive this learning rate schedule here. So first, what is this river valley landscape? So it's like you have valley, and then so valley is like the bell shape Gaussian distribution we have, and then river is the flatter regime, the river bed. So that's the river valley landscape. And via this landscape, they are talking about two time scales. One is the fast decay, which happens along the valley, and then the slow dynamics, which is happening along the riverbed, which is a flatter regime. Okay. Now, the toy model they use is this loss function, which is, again, they split this loss function into fast loss function and slow loss function. So this is the fast part, where A is the curvature of the valley, and X is some fast variable, and Y is your slow variable. And then this is the how the slow variable varies. So the thermodynamic analogy they're trying to make is that you split your loss function into this fast and slow.
So both X and Y are trainable variables here, right?
Yes.
Okay.
Yes.
And
yes.
by curvature, you mean this, it's not.
So like we also talk about, like there's a slope that you start with a high energy state and finally you reach some local minima. So that curvature. So it can be. So
Right.
initially
it's not
they
geometric
take
curvature you're talking
yes,
about.
geometric. Yes. So
It's
like
it's
you
not
have
geometric curvature, right? So it's not a geometric curvature. It's a
no,
curvature.
it is actually geometric as well. So it's like you walk through the canyon, right? So the floor of the valley can be narrow or it can be wider like this. So along the x-axis, then the curvature will vary. So
Well,
the
curvature
geometric,
is usually defined once you have metric specified. From metric, you can define the Riemann tensor, and then you can define Ricci scalar, and that would be curvature. So I think that here it just means this coefficient next to the quadratic term. It's not the geometric quantity here.
So when they are considering is anisotropic, then you have A varying. So it's not just fixed A, it is AI. So it is varying. So
Right,
there is an anisotropy at A as well.
But
So
yeah,
then
but
it
that's
is,
not metric. It's not you don't have geometry here. So it's you can have A varying from place to space. So this is like mass term. A is like mass mx squared. So it measures the the potential stiffness, but not there's no geometry here, as I understand. Because geometry comes with metric, and if there's no metric, there's no geometry.
okay.
It doesn't matter. This is just how they call it, so that's fine.
Yeah.
Mm.
So the thermodynamic analogy they're trying to make is that if you calculate your internal energy, it is heat plus work. So heat is the fast fluctuations that happen in the system, and then you do the work done, which is a slow process. Now, as I said,
sorry, there is more. So you also say that the fast variables will be associated with the heat, and
yes,
the slow variables is associated with the work.
yes.
So it's a strange way of defining heat and work. Usually, it would be defining once you specify your thermodynamic variables, then you'd say heat is contribution to the internal energy due to changes in the entropy, and then
Yes, so basically the
work
slow
is due to
dynamics.
changes in the volume, right? But here it's something else.
No, so the loss in the slow dynamics is basically what I'll explain later. It is the entropic force that is happening, and I'll explain it. So the slow dynamics is happening via entropic force.
That's strange because down here it says Ls is like work, not and the entropy is sitting in Q in the heat. But anyways, maybe for now it's not a precise map, so we can probably go on and then later figure out what that means.
Okay. Okay. Now, like I said, they separate the fast and the slow dynamics. So the fast dynamics happens along the valley. So let's first start with what happens in the valley. Okay, so in the valley, if I use this Langevin equation where you have this deterministic term and the noise term, so you can understand it like this deterministic term, which is A here is the, like I said, the curvature in the valley. So this curvature will lead system to go down and reach some equilibrium state. And then this noise is like the thermal noise in the system. Okay. So eventually this when the system reaches equilibrium, what is the role of learning rate? So eta is a learning rate, and it is trying to satisfy these two terms, the noise in the system and the deterministic pull, which is shifting system towards equilibrium. So this variance, what we have to do is we have to minimize this variance to minimize the loss function in the system. Okay. And this variance, it depends on the learning rate as well as the curvature. All right. For simplicity, right now, in this loss function, they just consider only x dependence, and they don't consider the y dependence. Okay, and they approximate that the curvature is it is approximately in the flatter regime. And in that case, your loss function is the key takeaway here is that your loss function is proportional to eta, which is your learning rate.
Hold on, I'm again lost. So in the equilibrium, what you want is xt plus 1 is equal to xt. Is that what you want? We mean by equilibrium when the states stop changing?
Yes.
Okay,
When the
so
states.
then the axt plus this noise term in your first equation has to be 0. That I understand. And what I don't understand is what is this sigma squared? Is where does it come from?
So basically, this has some Gaussian noise in the system. Okay, so finally, when you reach equilibrium, it is like a what do you call a bell-shaped curve. So you have some mean zero and some variance in the system. You don't reach the global minima. It's some distribution around which you reach.
Okay, so maybe what you're saying that xt is some
it's
random variable and then wt is some
yeah,
random
so
variable.
xt has some distribution.
Okay. And you're
It's a
saying that
Gaussian
the
distribution.
two random variables are related this way.
Yes,
Okay.
yes. And your loss function, like I said, the loss function is proportional to your learning rate. Now, this function, then they try to make analogy with the thermodynamic relation, which we know. So your loss function is directly related to eta, and it is not related to A. A is the curvature in the valley. So the whole point here is that the curvature of the valley does not affect the loss function. It is just the learning rate. You can assume, so like we have in the equipartition theorem, all degree of freedoms contribute equally to the amount of energy. And that's what is happening here. The fast dynamics that is happening in the valley, they all contribute equally to the loss function.
Do you understand why the learning rate is proportional to the loss function? Usually learning rate is some separate thing that appears in stochastic gradient descent. Now, of course, you can move. Yeah, so there's no learning rate here, right? So this loss function.
Yes. So you have 1 by half ax square, right?
Yeah.
Half ax square is your learning function for the fast decay.
Yeah.
And your x here is it has some variance.
Well,
which is defined here.
it has variance because WT has variance because
Yes,
you
yes.
have random noise.
Yes. Yes. So basically, your learning rate is trying to what you say balance between this deterministic force.
I think I understand it. It's not the loss function; it's the average loss function that depends on the fluctuations. It's expected.
Yes, it's
or average. So it's not the loss function.
Yeah,
Loss function, of course, doesn't depend on the learning rate. So what you're saying that if you have a larger learning rate, the system start jumping more around minima, and therefore its loss will be.
It's the thermal loss. You can say that it's the thermal loss in the system because of
sure, average loss. Average loss
yes.
would scale with because it's not equal. It doesn't stay in the minimum. It jumps right around. Okay.
Yes, exactly.
That makes sense. Okay.
Yes. So the analogy is with the equipartition theorem. Like I said, that there all degree of freedom contribute equally to the energy. Here, all the so you don't have any dependence with the curvature of the valley. That means all are equally contributing to a loss function. So what we can take away is that this loss function is analogous to energy, and the most important point, your learning rate is analogous to what temperature does in thermodynamics. Okay. Now, to sorry. Yes. So now to validate their point that this learning rate is proportional to eta, they did a test on GPT-2 training. So they use this model and then study the model and to validate that this kind of so your loss function is linearly related to eta. So here are the results. So you have learning rate on y-axis and your training steps on the x-axis. So initially the system warms up, then it reaches some flatter regime, and then it decays. Okay. So what they argue is that if you look at not very small eta min, then for those regimes, you see that the learning rate is linearly related to eta min. And similarly, if you look at delta L versus delta eta, there also you can find a linear relation when delta eta is small. So
I
from that,
don't understand this picture. So learning rate is something you control in your simulation. You can change whatever you want.
yes,
Are you saying that if you increase the learning rate, then the decrease in the loss function will be larger, right? So
yes, it's just like if your
but
temperature is,
that only works in the equilibrium again. So if now
yes,
and it's just again statement about jumping around local minima. So it's not a statement about. I don't think it's related. It is related to temperature, like in some naive sense. But temperature should be defined as the change of the energy with respect to change of the entropy. So du ds is what temperature is. Here, here they just say, okay, well, there is a linear dependence of the average loss with respect to the learning rate. But I mean, it's trivially there, of course. But why would you call it the temperature? I think this is what the statement is. Yes, learning rate is a function of temperature, but temperature isn't the learning rate usually. It shouldn't be. They are convinced that it is a temperature. Yes. So,
yes, I mean that's what the analogy they're making.
And this
learning rate.
analogy works well in the equilibrium, and it doesn't work far away from equilibrium, which also
Yes, around, yes.
to take and it only works in the quadratic limit of the fluctuations around local minimum. Yeah, that makes sense.
Yes. Yes. Now, next point is that why not just decrease, if I want to decrease, make my learning rate as a function of time, why not just decrease it too fast? So this also has an analogy with the thermodynamics. For example, if I'm I'm at a very high temperature state, right? Now they're saying learning rate is related to temperature. So let's make the analogy more clear. If you are a very high temperature state, and let's say I want to go to a crystalline state. So at high temperature state, my T is very high, and at crystalline state, my temperature is very low, right? If I quench the system from high temperature to lower temperature, I won't reach the crystalline state, right? I'll reach some disordered state like glass, and I'll get stuck there. But if I decrease my temperature slowly, like we do temperature annealing, if I slowly decrease my temperature, then I might not reach the crystalline state, but I'll reach very close to that state, right? So instead of quenching, if I use annealing, then that's a better way to reach the equilibrium state. And the similar thing is they are happening here also. So, sorry. Hello?
Yes.
Sorry, I'm sorry.
Oh, that's fine. Okay, so they say that annealing makes sense, and we know that, and but the result is that not only annealing, the learning rate should be decreasing as 1/t. That's kind of the result they have, right?
Yes. So basically, the point here is that you again have this Langevin equation where your learning rate is varying with time. So you want to go from a higher energy state to some equilibrium state. So you want a smooth the energy should go smoothly, right? So how will that happen? So to do that, you have to vary your variance at every step. You have to reduce your variance, and to minimize your variance, you need to have an optimal eta, right? That's the learning rate. And they derived that this should be the optimal eta here. And with this, what they argue is your eta is inversely related to time, and hence your loss function is also inversely related to time. So slow annealing ensures convergence toward minimum thermal loss. That's what they argue.
Yeah, but we know how the variance should change, and that is all the point of this Adam algorithm. Is the Adam algorithm? The point of it is to actually make this variance, decrease appropriately. Actually, it has to stay fixed variance until the system learns certain direction, and then it should quickly thermalize like in a stochastic gradient. So we actually know how to do that better than the just time dependent 1/t with unknown coefficient in front. Have they mentioned anything about Adam? Because this seems to be exactly
no, they talk about
because
something
they're right. You have to control the
yes.
variance.
No, here they're just trying to make basic analogies. They're not claiming that this is like
No, but we know that the variance has to be certain. It has to stay fixed, and then has to suddenly decrease, and that works very well. And that effectively changes, of course, the learning rate. This is actually they call it as an adaptive learning rate. So so they haven't mentioned anything about Adam.
no.
Okay.
Okay, so finally, the point is that the learning rate has two thermodynamic roles. One is the temperature, which I initially described, and then is the time scale. So the temperature is taking care of these fluctuations that are happening in the system, and the time scale will tell how the system converges to the equilibrium state, right? Now, to make this point even more clear, they now split their learning rate into two parts. So eta has now is split into eta A and eta B. So eta A is the high temperature state where the system equilibrates fast, and eta B then is the lower temperature state where you have slower convergence. So what they're trying to say is like you have a hot object which is in contact with a cooler object, and then the heat flows from hot to cold. And that's what happens in annealing also. You start with a higher temperature state, you equilibrate that system, then that equilibrated state goes to a lower temperature state as an initial state, and then it equilibrates to that lower temperature state, and so on. And that's how you go from a high temperature to a crystalline state, right? So that sort of an analogy is what they're trying to make here. And then the point is that, let's say you start with what I gave the example, exactly the same thing. You start with a higher temperature state, which is the higher learning rate state. You thermalize the system there, and then you switch. That means you go to lower learning rate, which is eta B. So how this evolution from a higher uh, uh, state to lower state takes place, it is given by this equation. And the solution of this equation has this exponential function, which we also know that if you relax the system, basically from higher to lower, the relaxation has an exponential behavior. But what they're trying to convey here is that you start with a higher temperature state, but the final evolution or relaxation towards the lower or cooler state is governed by the learning rate, lower learning rate. Basically, that's the point here. And then the analogy is with the thermodynamics is this how we know that heat flows from a higher temperature to a lower temperature state, and then the thermodynamic law. So basically, like I say, you are going from a higher learning rate, that means higher loss function, to a lower loss function. So there is a limit here that it since it is heat flow from high heat you're going from heat to cool. That means your loss function cannot be less than the loss function you have from eta B. That's what you get from the second law of thermodynamics also, which means that the entropy increases when you evolve towards equilibrium. Basically, you will never have heat flow from cold to hot, you will only have heat flow from hot to cold. And the gradient noise is the thermal agitation, and the learning rate is trying to cool the system by reducing this noise. Okay, and then this the loss decay is towards this lower learning rate. Now
How do they
to
separate the LF and LS? So in their analysis, how do they decide what are they going to call a fast variable and what they're going to call a slow variable?
So basically, whatever I'm currently talking, it is all fast.
Okay.
This currently they're using this loss function. This is only
Okay. Okay. So, but in the simulation, are they claiming that there will be like gap,
so for example, this is
energy gap?
when they're validating their theory, they consider this as a loss function. That's it. They don't consider the other part of the loss function, just this. So this is for the isotropic case, and for the anisotropic case, they consider this as a loss function. So the second part of the loss function is not considered in the simulations.
Yeah, it's quadratic loss function. Yeah, I understand that.
Yes, so this is your full loss function.
Right.
They don't consider this part in the
Okay,
simulation.
so are they? So they're only doing for the toy model of quadratic loss function.
Yes.
Okay.
Yes.
Okay. So
Yes.
then
Just this.
that's why they
Yes.
don't have geometry, because of that. They only have it's a fixed metric.
Yes.
They always change
Yes.
variables so that it becomes completely flat. Okay, now I understand.
Yes, just half ax square.
Okay.
That's what they
Okay.
consider throughout the. So this part is not considered at all.
Okay.
So to validate this optimal decay theory which they gave, so they again consider this loss function, and now this is the optimal schedule according to Den. And they find that the optimal value for B is 0.5 and TH is, I'll show you the graphs and then I'll explain it better. So the whole point of this slide is that this is your loss function and this is your optimal schedule for isotropic case, and for anisotropic case, again, the loss function changes, but learning rate remains the same. And for both the cases, what they show is, so in the first, they vary B and fix TH to be 10, and they find that the loss function is minimum when B is 0.5. In the other case, they fix B to be 0.5 and they vary TH, and the loss function is minimum when TH is 10. So now the parameters are B is equal to 0.5 and TH is equal to 10. So this heat map is for the isotropic case, and when your loss is minimum, that is the darker regime, here they show that B is 0.5 and TH is 10. For the anisotropic case, they fix their B to be 0.5 and vary their TH, and they show that again, it is whether isotropic or anisotropic for both cases, with this learning rate and the same parameters, they find the loss function, minimum loss function with the optimal decay schedule which they proposed. Now,
but the point of Adam and other advanced algorithms that you should not have the same learning rate in all directions. So in the case of an isotropic case, it should be adjustable to in certain direction you have one learning rate and the other effective learning rate and the other learning rate. But in this case, they're just assuming that the learning rate is the same in all directions. Yes?
Yes.
Okay.
So now, up till now, I was only talking about the dynamics happening in the valley. Okay. Now they talk about what happens along the riverbed. Okay. Now in the, like I said, the riverbed, what happens there, you can imagine it by, if you consider moving around a canyon. So along the floor of the valley, you'll have narrow regime, wider regime, and so on. So the movement there, that's not because of any gradient, or that means any any gravity or anything. That's because of entropy. What it means is, let's say you start with a narrow region, you try to move forward where you have more space. So you from narrow you go to a wider region, okay? Because there you have more space to move around. Here they explain this that by this curvature AY. So when you have a narrow valley, that means you have a high curvature, and a broad valley means you have not like a flatter and a broader region. Now that affects your variance. Okay, now you have this full loss function, and if you have high AY, then your variance is small, and vice versa. So this they relate with entropy. Now we already know that entropy increases if you have a high number of microstates, and that they relate with this variance in the curvature. So if you have a very narrow valley, that means your entropy is small, and if you have a wider valley, then your entropy is large. And this they relate with the force. So basically, what they're saying is that the riverbed, the motion in the riverbed is related to what happens along the floor of the valley, and that leads to an entropic force which will affect the motion in this riverbed. And this for this they tried that whether any entropic effects can be seen in the LLM model. And what they test is that so each line here that corresponds to various learning schedules, which will so again you have warm up, decay, and some warm up, steady, and then decay. I didn't have a very good understanding how they show it, but what they wrote is that you have this warm up and then stable and then decay. So the eta min for all three these three schedules is same, which is this, which is around 0.006. But the max for each is different. So you have three different max. You can say that there are three types of schedules, each with different final learning, each with same final learning rate, but different peaks. And then what they calculate is loss versus sum of the learning rate. They don't calculate individual, but the sum of it. And they show that the data almost overlaps. What they mean by this is that it's not the peak of it's not this peak which peak of the learning rate that matters, but the accumulating effect of the learning rate, so the summation over them. So they related to basically the total entropic exposure that affects your loss, and not just the maximum learning rate. That's what they argue.
So I think I'm lost a little bit. So what's the test? The test is that they take a large language model,
Yes.
GPT-2, and they're trying
GPT-2. Yes, yes.
GPT-2, and they're trying to train it with a schedule learning rates or no?
Yeah, yes. So they have
What's the
different
schedule?
learning rates. Sorry?
The learning rate is changes with time.
Yes.
Okay, so and there's a predetermined schedule for the learning rate, like they had before, or something else? Because the learning rate here experiences very strange behavior.
Yeah, that's what I said. I couldn't understand this plot very well, but that's what was written in the paper, that they have
Isn't this the schedule? So like, before the learning rate was some function, 1/1 plus t, something like that.
Yes, yes.
So here it's not 1/1 plus t. So its first learning rate grows linearly. Then it makes, I don't understand.
Yeah, so basically in principle it should behave something like this. So your initially there is some warm up. That's what they say. This is the standard behavior in LLMs models, that initially the learning rate linearly increases, then there is some stable state here, and then it decays. So this warm-up flat decay, that's a common behavior seen in
Okay, this
LLM.
is not behavior, this is common schedule, right? So learning rate
common
is a
schedule.
schedule.
Yes.
So it's common
Yes.
schedule. Okay. And now
Okay.
they're trying different schedules.
Yes, and now they're using various learning rate schedules, each with some stable eta max. That means this. So each will have this stable eta max.
But not only
Okay.
that, it warms up, then goes down, and then gradually goes up. So it's completely different from what people do in the large language models. Then what's the reason of using this schedule is not clear. It's not clear why they use this, first go up, then down, and then gradually go up again. What's the reason for all that is not clear. I mean, if they want to just measure entropic force, they can, of course, do that for any training, learning task. It's not. I mean, we've done that certainly.
So basically, I think the point they were trying to make is that this so how will they detect this entropic effect? So the arguing is that to detect it, you need to look into the cumulative effect. Cumulative effect means you have different learning schedules which can have different peaks as well, and then you average over it. That's what this plot is showing. So I think that's what is done here also, that you go with different learning schedules. Although here you
can get this entropic force just by changing the mini batch size. The mini batch size, by making it smaller, you have more entropy in the system. Let's just start jumping around. Not even changing the learning rate, just keeping the learning rate. By changing the mini batch size, you can have the entropic force. So if their only objective is to show that there is an entropic force,
yes, that was the objective.
Then there, you don't need to implement this fancy schedules. So anyways, for me, it's a mystery why they use this schedule for now.
Yeah, but the aim here was just to see whether LLM show any such entropic effects.
Yeah, I agree with the conclusion that there is entropic force. Yes. Okay.
Yeah,
thanks.
and but very weak entropic force. That's what they argue. And they argue that there is weak entropic trapping.
Weak entropic force. Well, it depends, right? Okay, very good.
And finally, they map it like this. Like I said, that this is a loss function and corresponding thermodynamic maps. And here they show that learning rate is corresponding to temperature, like I said. And that's how they do the mapping from LLM to thermodynamics.
Perfect. Thank you.
Thank you.
There questions?
Yeah.
Go ahead.
Like when I took a quick read of the paper, I thought it was going to be something a little more more precise, but it's more of an analogy, right? That kind of makes sense, kind of works.
Yeah.
I wonder if some of it can actually be derived from the StatMech framework.
I think you can derive it starting from scratch and from defining what we all know, temperature, we know what temperature is. The only thing you have to postulate what the average energy is. And, average loss seems like to be a good thing, but everything else you can derive by following the statistical ensembles and then seeing how things work. So yeah, so I agree this can be made a lot more precise, way beyond the toy model. Okay. Other comments? And especially I want to see, we've showed the connection of all of those variances with, efficiency of learning. You don't need to have all those schedules you can just define a metric, and that's what we did with Dmitry in the recent paper. So on the covariant gradient descent, you can just define all those. Instead of just specifying the schedule, you can like calculate on the go what the effective learning rate should be, and then yeah, it will be very anisotropic. It will be different in different directions. Okay, well, anyways, interesting that other people are also thinking about thermodynamic applications, using thermodynamic tools to understand machine learning systems, and that's very interesting.